Hello, and this is going to be a video on organic chemistry. Now this is going to be split up into 4 lessons. This is for triple and combined, but triple have more content and I'll do those videos after. So, first lesson we're going to do is hydrocarbons. Second one will be what we call fractional distillation, and that is all about how we separate out the crude oil. Let's put that wrong. Okay. And the third one will be on burning hydrocarbons. And the fourth one will be on what we call cracking. So that will be all of the combined organic chemistry topic. As I said, I'll do triple only content later on. So we'll start off with hydrocarbons. So put that as your title for your note and we'll move on from there. So first of all, what is a hydrocarbon? And it's quite simply hydrogen and carbon. It is just compounds made of just those two things. Now later on there will be more additions to this, mainly for the triples. I'll talk a little bit about the combines, but mainly for triples. Now an example will be methane, which is the stuff we get out of our gas taps. It is a single carbon with 4 hydrogens around it. Now carbon is in group 4, and that means it has 4 electrons in its outer shell. 1, 2, 3, 4. I haven't drawn the circle, but as you can imagine. Now it wants to share, so it's covalent bonds, to reach 8. So hydrogen each has 1. And as you can see, we now have 1, 2, 3, 4, 5, 6, 7, 8. 8 electrons, and therefore it has reached the 8, and it is stable. So this is the most basic of our hydrocarbons, and it's what we call it, as I said earlier, methane. So methane only has 1 carbon, and that's applicable to any other hydrocarbons, which we'll talk about later on, but methane is the most basic and only has 1 carbon. Okay? Now next, we're going to talk to you about all of the different hydrocarbons. So let's clear that up. So we got methane, that is CH4, 1 carbon. We have ethane, that's our second one, and that is C2H6, 2 carbons. And then we have propane, and that is C3H8, 3 carbons. And finally, the last one of the odd naming is butane, and that is C4H10, 4 carbons. Now after this it gets easier to name, it kind of goes with shapes. We've got pentane, so pent being 5, hexane, heptane, octane, oct being 8. So if I'm going to draw out this one, as I drew out on the last page, and I'll show you. So we've got 1 carbon, 2 carbons, 3 carbons, 4 carbons. Now each carbon will want to make 4 bonds around it. So next step is to draw the lines, because these lines represent the bonds. And then we've got 10 hydrogens to place around here. 3, 4, 5, 6, 7, 8, 9, 10. And that is what butane looks like. 4 carbons in a chain and 10 around the outside. Now these are what we call alkanes. Okay? They are just carbon and hydrogen with what we call single bonds, in between. And I will touch upon double bonds later on in the last lesson, in lesson 4, but for now, you see they're all single bonds, just a single line representing a bond. Now, they're also, because these are all alkanes, they're what we call a homologous series. This is just a series of hydrocarbons that have similar properties and similar look to them. They look the same, similar shape, you should say. So that's our alkanes as a hydrocarbon. Okay? Next, we will move on to what we call fractional distillation. One thing before we move on, there is what we call a general formula for all of these, and this is CnH2n plus 2. Now, n equals any integer or any number. So if we use this to help us out, 2, we change n to a 2, but C2H2 times 2 plus 2 equals 6. It fits. We'll do it with 3 this time. We'll put a 3 here and a 3 here. 2 times 3 gives us 6 plus 2, 8. It fits. So this is what we call a general formula, and it fits the pattern for every single alkane. So this is the alkane general formula. It allows us to work out the number of hydrogens and the number of carbons for any alkane, whether that is methane with only 1 carbon all the way through to 1,000,000 carbons. We can figure it out. Okay. Right, let us move on to fractional distillation. So we'll call it fractional. So this is a process to separate crude oil into different fractions. And what I mean by a fraction is a group of similar length hydrocarbons. So for example, methane being CH4 and ethane being C2H6 are similar in length. There's only one between. And to be honest, even propane with C3H8, these are all similar. This is what I would call a fraction. They have similar properties, similar boiling points. And boiling points is the key part to this. Okay, so let's talk about actually what goes on in fractional distillation. Now this is done in giant plants, power plants, and it's not done in a small scale, but it can be done in a school lab. However, I can't show you that right now. But what will happen is we will have a giant vat. And it should look a little like this. So, and if you've got these different sections, wind also we have a bit coming out the top. So this is our overflow. I'll explain that. So we have superheated crude oil is sent in at the bottom. Super hot, okay? Now let's just say, for example, this is 350 degrees centigrade, this is 250 degrees centigrade, this is 150 degrees centigrade, this is 50 degrees centigrade. So what happens is superheated or crude oil comes in, and if even at 350 degrees in this chamber here, it turns into a liquid, it will settle at the bottom and it will run off. So this will be a very viscous, and by viscous I mean quite gloopy, thick like syrup, viscous liquid. Down the bottom is generally what we call bitumen, and it is tar for roads. It's got a very high boiling point, and it's got a long chain, but I'll go into the chain length in a moment. Now, if it stays as a gas, it will go up, and it will come up to here. Now, if it turns into a liquid here, okay, it will get siphoned off. The bits that still stay as a gas go up, and if it comes into a liquid here at 150 degrees, it gets siphoned off. And up to the final section, if it turns into a liquid at 50 degrees, it comes off. And now if it stays as a gas, it will come out the top. So a gas is, the final bits will leave at the top. And that'll be things like your ethane and your methane. Now this is how we separate it out. We have temperatures getting cooler and cooler and cooler as we go up. And if it turns into a liquid at these different temperatures, it will get siphoned off. Now things like petrol are going to be around here. We'll have diesel, kerosene, around here. There's lots of different ones. You can find them on BBC Bitesize, you can find them on a long list, but you don't need to know it in detail, you just need to know the process. So it all comes in as a gas, and if it turns into a liquid, it'll come running off down here. If it stays as a gas, it'll go up, liquid, say a gas up, liquid, and so on. And that is the process for fractional distillation. Now we're going to quickly talk about length of chains in regard to this, because that is an important part. So the longer the chain, the higher the boil point. So long chain, and by chain I mean lots of carbons together like this. That's a chain of carbons. So a long one being 20 plus, let's say, will have a high boiling point. And that means it will be a liquid even at this high temperature. So this is our long chains. They are unreactive. They are viscous, as I said earlier. They are gloopy like syrup. They are unreactive, low velocity, viscous. They don't burn cleanly, and I'll talk more about burning in the next lesson. Whereas at the top, they are short chains, so that is our methane and ethane. They are reactive, open brackets, volatile, that literally means reactive. We will have, there will be gases, and so opposite of not viscous is not viscous, easily flowable, and burn cleanly. And this is a scale. As you go further down, you get less reactive, more viscous, and you get more of a dirty flame as they burn. So that, in short, is fractional distillation. It is a method by which we separate our crude oil. Crude oil comes from the ground, it comes from under the ocean, we drill it up, and then we separate it out into the useful things that we need. Because there's a huge mixture like that, it's not very useful, but ethane and methane is useful in school for gas, petrol is useful for cars, diesel can be useful for trucks and lorries, kerosene is for planes, so bitumen down here is useful for tar, for houses, for roads. Okay, so that is fractional distillation. Now we're going to move on to burning of hydrocarbons. Burning hydrocarbons. Hydrocarbons burn very easily in oxygen, a good presence of oxygen. So let's have a look. Let's imagine we're burning some CH4 and it will burn in oxygen. If you ever see this sort of reaction, an alkane and oxygen, that is what we call combustion reaction. And that's pretty much another good name for this. Combustion. And it will make carbon dioxide and water. Now this is unbalanced. We'll have to look at balancing that as we go. But as you can see, it is quite a simple equation. So let's put 2 here. Now got 4. Okay, so that should now be balanced. Right, now this is what we call complete combustion. It's with a clean flame. And what I mean by clean flame is there's no like black soot in it, so no black soot. It is a very nice blue and orange flame because we have a complete amount of oxygen. We have enough. Now, in complete combustion, we have a lack of oxygen. Now, if we look at our products, we've got CO2 and we've got water. Now, this time in incomplete combustion, because we don't have enough oxygen, instead of making CO2, we'll make CO. Or in some cases, just C. Now this is soot, and that's why we get no black soot. In this one incomplete, we get some black soot. On this is what we call carbon monoxide. And this is the silent killer. It's dangerous. You can't smell it, can't see it, and it will slowly kill you because it blocks oxygen getting into your cells, in short. So this is what we call incomplete combustion. It's not got enough oxygen, so we can't make CO2. We have to make CO, or in some examples, C. So that is the 2 different types of combustion when we're burning hydrocarbons. Now this can be for any different hydrocarbon. It doesn't have to be methane, it could be ethane, propane, butane, etc., etc. But the longer the chain, the more oxygen we need. So actually what we find is that we get more of a chance of incomplete combustion with the longer chains, and that's why you get that dirty flame as I mentioned in the fractional distillation part. So a longer chain equals more oxygen required. So these are the two different types. We've got complete, we have enough oxygen, we have more than enough oxygen, and it will happily burn with this and will make carbon dioxide. Water. Incomplete, we have a lack of oxygen. Right, now let's move on to the final part. Let's move on to cracking. Cracking. So cracking is a process by which we take a very long chain, so a long chain hydrocarbon, and we thermally decompose into smaller chain hydrocarbons. So, thermally decompose, we use heat, breakdown. So we use heat to break it down from that long chain into that smaller chain. Now that doesn't mean we set fire to it. Do not set fire. But it does mean that we heat it up. Because if we set fire to it, that is a combustion reaction, whereas thermal decomposition is breaking it down using heat. And you'll have a setup that looks a little bit like this. You'll have a test tube. Let's try that again. We have a test tube, and in the test tube we'll have some of the hydrocarbons, so we'll just say the hydrocarbon down here, and we'll add some heat. And as you can see, I'm not burning it, I'm heating it from outside the test tube. And we'll have a bung in the top. With the bung, we'll have a tube running through. Now this tube will send down into some water, and we use this in what we call a water bath, and this will cool it down because it's going to be very hot as it leaves the test tube. So we're going to cool it right down in a water bath. We'll collect it in another test tube. Now this test tube's been inverted in the water, so it's got full of water, and as the bubbles go up, it pushes the water out, and we're left with just hydrocarbons, short chain hydrocarbon at the end. So we heat it, it breaks it down because it's thermally decomposing, and it will travel through here and into this new test tube. We can get whatever the product is out here. So that is our method for cracking. Now we need to look at the actual reactions behind it. So let's say we're going to crack C10H22. That's following our CnH2n plus 2 rule. And this will break down into two smaller hydrocarbons. Now, in the exam, you might get asked to draw the products. Now, the products could be anything that you like, as long as the carbons add up to 10 and the hydrogens add up to 22. So let's say we'll break it down into what we call C2H4. Now this one looks a bit weird, and I'll talk about this one in a moment. Plus C8. Whatever's left over will be 18. So we've broken it down to two smaller ones. Now this one is not an alkane anymore. It is an alkene. And I'll talk a little bit about those in a moment. But this is one example. We could have done C3H6 and C7H16 if we wanted to. But as long as all the carbons add up to 10 and all the hydrogens add up to 22, It doesn't matter what we draw here. Now, one of the things we make is an alkene. Now this is extremely useful. And this is why we do cracking often, to get this alkene. Because the alkene has what we call a double bond. And it will look a bit like C. You can see the single bonds of hydrogens, but then that's that double bond in the middle here. You see the two lines representing it. Now the double bond makes it quite reactive. And that's useful because we can make other things out of this. We can break one of the bonds and attach other things to the carbons to make new parts. So an alkene is extremely useful. So the alkene's general formula is CnH2n. It's just double. We don't plus 2 this time. We just double it, as you can see here. This one we doubled plus 2. This one, as being an alkene, we just doubled. So that is the general formula for an alkene. Now we test. You need to know how to test for an alkene. So the test for alkene. Because how do we know that we've made an alkene when we've done thermal decomposition? What we do is we add bromine water. We add bromine water. And this will go from orange to colourless. And I'll talk about this just a bit more now. So we add bromine, so let's show you this again. We're going to go C, double bond C, and we're going to add some bromine water. We'll just put this as Br2 because bromine water literally means bromine soaked into water, but the water doesn't play a part. And it goes to form the following. So this time the bromines have come across and are bonded to the carbons. We've lost the double bonds, as you can see here, double bond, and we've lost it. So that is why bromine water shows us if we have an alkene present, because we break the double bond. If you placed it into an alkane, nothing would happen. So the reason is we go from orange on this side. This is the orange part. Bromine gives us a lovely orange colour, and then once it's like this, it's colourless. And that change from orange to colourless shows us we have an alkene with that double bond present. Right, that is a quick overview of the organic chemistry topic for the combines and triples. Triples will cover more content after this, but I'm going to put this onto Google Classroom and you guys can then have to go over some worksheets afterwards. Thank you.